More than 20 years have passed since the announcement of advanced encryption standard, and it still withstands every cryptanalysis technique we know. So it is secure, and crypto community thought that we don't need any other block cipher because we kind of have a very good one, almost the best, and we can use it in almost every environment and be happy with it. But a paradigm shift in computing and information technology made us to design other ciphers, and actually we will call this area lightweight cryptography. So let me explain why this is the case and why do we need some lightweight cryptography. Actually, I will also define what we mean by lightweight cryptography. So initially, when the computers were first built, let's say there were generally one computer and many users connect to that computer via terminal, and so for this reason we had initially one computer and many users. But after the personal computers, we moved to an age where a user has a computer, but now we are in the age of many computers, one user era. So, and this is also accelerated by the Internet of Things. So almost every device we have has computation capability, like smartphones, smartwatches, etc. But we also have a lot of small devices too. Even the lights at your home now may be turned off or switched on or off by a mobile phone application and so on. So we have a lot of devices by many computers. I'm actually referring to any device that has computational power. So many IoT systems run on resource-constrained platforms. For example, mobile tokens without battery, RFID tags, medical implants that do not allow to change your batteries. Many IoT devices are extremely cost sensitive because they are deployed in extremely high volumes. So actually, this is the problem. You want to build them in a very cheap way, but due to this, a lot of IoT devices are built without security in mind. And most of the IoT devices don't have actually any security at all. So industry needed lightweight cryptography for at least 20 years, but it became an active research area in academia over the last 10 years. Thus, industry deployed several proprietary self-made algorithms and many disasters happened. Some famous examples are keylog, which is actually used for remote keyless entry, like garage doors, but also cars. So you could easily actually unlock the doors of a car and steal it due to an attack to this keylog algorithm. MyFair Classic is another example. This is one of the world's most, I think, built smart cards, and it has serious weaknesses which it can easily clone. So for this reason, crypto community decided to develop lightweight algorithms, and initial designs mainly focused on low hardware footprint, but it is not realistic to have a single cipher to satisfy all needs. By all needs, I will explain what other things we need. To fit within constraint settings, lightweight ciphers rely on simpler round functions or minimal key schedules. The simpler structure of many of these ciphers may lend itself to new attacks. Actually, a lot of new cryptanalysis techniques are discovered by analyzing these lightweight designs. Currently, we have 3 block cipher standards for lightweight cryptography. These are IOCL standards. Present and CLEFIA became the standard in 2012, but LEA is actually recently added to this lightweight block cipher standards. I think it was added in 2019. So I told you that initial designs focused on low hardware footprint. So as you can see, the first standards are always in this category. But later designs focused on some other cases like low low memory consumption on small embedded processors, so we have some ciphers for that. Print cipher focused on low latency, and we also have some designs which provide security against side channel attacks. Side channel attacks are cryptanalysis techniques that does not break the cipher itself, but that breaks the implementation. So it is on the attack on the physical implementation, but not at the theory of the cipher. So we mentioned that there are three standards: CLEFIA, Present, and LEA. Let's first look at CLEFIA with a simple picture. This is a generalized phase-style cipher, and there are 4 lines, as you can see here. This is why we call generalized phase-style. Otherwise, in standard phase-style, you had 2 lanes. So CLEFIA has 128-bit block cipher as block size. So all of these lines are actually 32 bits. So these it is a generalized phase-style network actually. So the run functions are here F0 and F1, but we are not going into detail in this course. So the recently added standard is LEA. This is not phase-style, but addition. I mean, it also looks like a phase-style, but it is addition, rotation, XOR structure. So LEA has also 128-bit block size. So each lines here represent 32 bits. As you can see here, there is an XOR operation with the round key, but there is a different symbol here. This is actually modular addition. So you are adding 32-bit value to 32-bit value here. So it is like a regular addition. But if you have carry bits after the 32nd bit, we actually disregard them. So this is addition modulo 2 to the 32. And these operations are rotation operations. This is left rotation to 9 bits. This is right rotation of 5 bits, and this is right rotation of 3 bits. So a very simple structure. I think this has 24 rounds if we use the key size as 128 bits. And the third standard for lightweight cryptography, the block cipher standard, is Present. I will give more detail about the cipher to visualize what is going on. So it is a very simple structure. As you can see, the block size is 64 bits. So each line here represents a single bit. So as you can see, this is an SPN design, substitution permutation network. So you have a key addition layer, substitution layer, and a permutation layer. So this layer provides confusion. This layer provides diffusion. So this is a simple XOR operation with the round key. Then you perform an SBox operation that has 4-bit input and 4-bit output. All of these 16 SBoxes are identical, and the SBox is defined like this. So these 4 bits, when you write them in hexadecimal notation, take these values. So you replace with the output value. So for instance, if all of these 4 bits are 0, in hexadecimal notation, this means also 0. But the output is C, which is 12 in decimal notation. So 12, if you assume that the leftmost bit is the most significant bit, then to C becomes 1, 1, 0, 0. So you should get used to thinking in binary and hexadecimal when working on cryptography. So this layer provides confusion. Then you permute the position of the bits and obtain a 64-bit round output. So you take this, put it here, and repeat this process 31 times. So it is, then you obtain the finally here with an additional key XOR, you obtain the cipher text. So you might think that, but what is the key schedule? Key schedule is for the 80-bit version is as follows. You take the 80-bit key and put it in a register as K, and left 64-bit of this register is always the round key. So initially the left 64-bit is taken as the initial round key. Then you perform these operations on this 80-bit register, and after these operations, the leftmost 64-bit becomes the following round key. And these operations are really simple. Here you're actually performing a 19-bit of right rotation to this 80-bit register. Then you apply a single S-box operation to the leftmost 4 bits. Then you add the round counter, you XOR with the round counter, and round counter is just the current number of the round. So initially it is 0, at the first round it is 1, at the second round it is 2. And key schedule for 128-bit present is similar. There are a few more operations. I just wanted to show you what happens when you perform the key schedule operation, when you choose your key all zeros. So 80 zeros in hexadecimal notation, it becomes 20 zeros here. So the leftmost 64 bits here are the initial round key, so they're all 0 too. Then you perform the operations I just mentioned. So next round key becomes this, then this, then this, then this, and so on. I'm showing you to show so that you can realize that, as you can see, there are a lot of zeros still. I started with all zeros. Since the operations are really simple, the diffusion is really slow. So for this reason, you keep seeing a lot of zeros in the key schedule. And finally, as you can see in the following rounds, you get something that looks more random. So with keeping in mind that this is the key schedule, let's use that key and take the plain text block as all zeros, and let's perform encryption to see what happens. So the first round output is this. The second one is this. As you can see, there are a lot of zeros here. This shows that slow confusion and diffusion. But when you keep going, you realize that the round outputs look more random. And at the end, you obtain the ciphertext block here. So this is important because we also use these values as a test vector. So if you implement present, you would want to check if you obtain these results when you encrypt all zero input with all zero key, so that you can find your implementation mistakes if there are any. So why do we need lightweight cryptography? Of course, it is we want encryption, we want encrypted communication, we want security. This is important. You might think that, of course, this is obvious, but a lot of IoT devices you buy actually don't come with encryption. So this is one of the problems. Sometimes they just use a hash function to provide security, but which is not encryption, of course. And this is also important in a lot of Turkish videos I hear in a lot of places. People talk about hash functions as if it is an encryption. So they say that, for instance, SHA-2 is a hash function. They say that SHA-2 cipher, but they are not a cipher. This is important, and I want you to warn everybody. So, of course, the main objective is the encryption, but the question is why we don't use AES, because most of the time AES might not fit in the device, but even if it fits, it might not provide us the throughput that we prefer. Also, we might need authenticated encryption. We might want to increase our battery life so that we have a cipher that consumes less battery life, which requires less energy. And we also need a cipher which has small latency, high throughput, and side channel resistance. So with these aims in mind, NIST actually communicated with academicians and people from the industry and held workshops for a few years to see if we need such a standard. And after all of these discussions and workshops, everybody agreed that we need such a standard, and actually we need it fast, because a huge disaster might happen. There are a lot of IoT devices on the wild which don't have any security at all. So for this reason, NIST decided to hold a competition. You can read this report. They actually describe the requirements they need, but here is just a short example from there. The evaluation criteria of the competition will be based on physical properties, performance, and security. By physical, we say we think about the area that it requires to be that it requires on the hardware. You can measure it with millimeter squares or gate equivalents. We also want, so we want them to be small. We want the cipher to require less RAM or ROM. We require small code size, both on hardware and software, and we also want them to require less energy. And the performance is based on latency, throughput, and power. We also require security. We want to, in the competition, the crypto community tries to cryptanalyze all of the candidates, and the broken ones are actually eliminated. So this was the competition so far. So it kind of, I mean, the competition actually started, I think, here, yes, August 2018, but the workshop started around 2015. The submission deadline was February 2019. So after that, first round candidates were announced. I think there were 56 candidates in the first round, and in 30th August of 2019, second round candidates were announced. There were, I think, 32 of them. And actually, in a few months, we are expecting NIST to announce the finalists. Actually, they were planning to announce them a few months ago. But due to pandemic, they decided to delay this choice. So there's currently performing benchmarks on the hardware implementations to see which one has better performance. So currently these are the second round candidates. So these are still in the competition. But while we're talking in this video, maybe NIST is planning to announce the finalists right today or maybe in a few weeks. But currently these are the algorithms that that are in the competition. So if we want to summarize, IoT devices are very different than each other, so it is hard to provide standards for all. So maybe I need to mention here something. When I say IoT device, everybody thinks about Raspberry Pi. But when I say constraint device, they also think about Raspberry Pi. But Raspberry Pi is not a constraint device, okay? It is no different than a computer. It has huge amounts of memory, a very good CPU, and so on. When we say constraint devices, we are really talking about devices which have very slow CPUs, very small amount of memory, and so on. For instance, 4-bit microcontrollers with memory less than even a Commodore 64. So think about it in this way when we talk about lightweight cryptography, not because any modern cipher will work really fast on a Raspberry Pi. So current device production does not focus on security, and this standardization process is going to take at least 2 to 3 years. And even if the competition ends and winner is announced, it takes around a year for that to be officially published and so on. So until that time, we will have really bad devices with no security at all. So be careful when you are using an IoT device. Producers should provide their own security solutions until IoT standards are available. We may need different lightweight ciphers for different purposes. Due to their simplicity, lightweight designs may be weak against attack types that are not discovered yet. But this is important. Lightweight does not mean shorter key. Using short keys provides almost no security. And in my opinion, there is no need to use keys shorter than 128 bits. So this is really important, actually. People think that since it is lightweight, the key should be short, but actually it doesn't. And this competition, NIST hasn't decided yet if they are going to announce one winner or more than one winner. So currently we don't know. Of course, the people who are in the competition prefer more than one winner so that they have higher chance of winning. But industry prefers to have single standard, because if you provide 2 winners, so 2 standards, when you build a device, most probably you have to put both of them in your device. So industry doesn't want that, because this is also against the idea of lightweight crypto. You cannot put 2 different algorithms and, save space. It is so this is why industry prefers a single standard for every IoT device.